Bismillahirrahmanirrahim. Assalamu alaikum. So, in this series of couple of lectures, I will talk about the different type of polymer, which you have. Some of them you have already seen, and some you will see now, and in more detail. So here we have three classes of polymer: inorganic, partially inorganic, and organic polymer. So this lecture 7 is composed of two parts, part 1 and part 2. So basically here I'm going to discuss about the inorganic and partially inorganic polymer, their synthetic method, and then important modification and uses. And then in the next lecture, the part 3, we will talk about the organic polymer. So as the name says, what are inorganic polymers? The polymer with the skeletal structure that does not include carbon atom. Means in the backbone you should not have any carbon atom. So that's pretty much the inorganic polymer. Look at this example here. For example, polysilane. This is one of the example. Look at here. All this backbone is composed of silicon. Silicon is also like a carbon with have four valencies. So like four valencies here and here. So this is the continuation point, and this is the monomer which connect to the next dimer, trimer, tetramer, and then so on. That's how you get a polysilane. Okay, so if it is asked you to write the repeating unit, you just choose one CH3 SiCH3, and here you put a bracket, and here you put a bracket, and that is the polysilane. And this is just I wanted to show you the sequence. So this is your inorganic polymer. Now partially inorganic polymer is the one that have some organic elements as like oxygen, nitrogen, or phosphorus, which is also present in the backbone. Okay, and these are also called hybrid polymer. Look at this structure here. The example is polysiloxane. Sil means silicon and ox means oxygen. So here if you look into the backbone, you have silicon and then oxygen and then silicon, oxygen. So in the backbone you have an organic atom, oxygen. Before that it was only silicon, silicon, silicon. That's why it's only inorganic. And this is the hybrid one, and this is also called a partially inorganic polymer. So you should be able to remember the basic difference between the two. And now the third is the organic polymer, and of course the one that have the carbon in the backbone. So if you look at here, this is the example of the cellulose. This is the monomer glucose unit, which is connected to this glucose unit, and this is connected to another one, and the chain continue from this side and from this side. And this is of course the carbon oxygen combination. So that's why it's organic. Okay, now in the inorganic polymer, we also studied this one before. We have two types of thing. Homoatomic polymers means only one type of atom, only one kind of atom in the main chain, means backbone. Heteroatomic polymer, when you have two or more than two types of atom in the backbone. So now some example of the homoatomic inorganic polymer. For example, silicon. So the backbone is silicon. Look at here, silicon has four valencies, so the one R will go here and one R goes down. Because I'm not in the class, so I cannot show you right now, but you should know this one, and you have learned this from the previous organic chemistry class. So you should be able to write correctly the position. So you put a bond here and put one R here, and then another bond here and put one R here, and then this is the continuation connected to the next monomer, and then and so on. Same here is called germanium. So in the backbone you have germanium, and then the tin or stannous. So that's the name of them. When they have silane, that's called polysilane, polygermanase, and polystannase, and this is their name. Now in some of the cases, when you have heteroatomic, means the backbone you have two atom kind of atom. Like here, look at here, silicon oxygen connection. So now in silicon oxygen connection, the name of the compound is called polysiloxane. See here, polysiloxane. Sil means silicon and ox means oxygen. So silicon is here. So the one R will go here and one R goes here, and this silicon is connected to this O, and then is O connected to another silicon, and that's how the chain will continue. So what you have to do here, make a sequence at least 3 or 4 monomer unit in your practice, so you know how to write this one, because this may be asked in the assignment or in the exam, how to write this structure. Now in this category, look at here. Here I have R here. If both R are replaced by methyl group, then the name of the compound will be polydimethyl, because one methyl group here, one methyl group here. So dimethyl, polydimethyl siloxane. So siloxane is the main compound name. Poly is the polymer, and dimethyl because of the two methyl group. Okay, now after that you will go to the next one, which is like a polymethyl hydrosilane. So what you will do here, this one I leave it for you, how to write the structure. Polymethyl hydroxyl, this is the structure, PMHS. So you have to write down the structure for yourself, and I may ask you to do this in the assignment. Okay, and this may be asked in the assignment to show. Now moving on to the next one is the silicon nitrogen. Silicon nitrogen means the compound name is called polysil. Sil means silicon, as is used for nitrogen, so polysilazane. So this is the R, this one goes here, R1 means first R, and this second R goes here, and third valency of silicon will go like this way, so the continuation of the chain. Fourth valency of silicon will be connected to the nitrogen, and nitrogen has 3 valencies, right? So the one R will go here, and the second valency will go outside. This is not 3 R's, this is just differentiating these 3 different R's, R1, R2 and R3. Does not means here you have 1 R, here you have 2 R, and here you have 3 R's. Don't get confused. I'm telling you one more time, silicon has 4 valencies. So one valency on this side connecting the nitrogen, remaining left 3. One will be here, and one will be the down, and the third one is the continuation of the chain, will go outside the bracket. Same for nitrogen. Nitrogen has 3 valency. One is connected to the silicon, the second one goes on top, on which you have R, and the third one will continue on going outside the bracket. Okay, so this is called polysilazane. Now when we say that per hydra per hydrid hyd, per hydrido polysilazane, per hydrido polysilazane. When we say this one, which means that all the R are actually hydrogen. So one hydrogen here, one hydrogen here, and one hydrogen here, then the structure will be made. So you should know how to write. I leave this structure for you to prepare yourself how to write the structure. Okay, and then we will move on to the next slide, which is also example of the heteroatom. Now the main chain is connection has phosphorus and nitrogen, phosphorus and nitrogen. So look at here, this is the phosphorus, so this valency going outside the bracket, so the bracket will come here, and the phosphorus has 2 OR groups, so one OR goes up, other OR goes down. R may be methyl group, ethyl group, or isopropyl group, and the phosphorus connected to the nitrogen with 2 valencies, and then the nitrogen third valency going out of the bracket. So you should be able to write the repeating unit structure with the help of the way I mentioned to you. Now here, this is the general formula. Now if I give you the name, this polydichlorophosphazine. So we know phosphazine is this P double bond N. That is the phosphazine main structure. Bracket here and bracket here. So this is the thing that can be replaced, and these things when replaced, the name will be changed. So what I said, polydichlorophosphazine, which means that this OR are actually replaced by Cl. So one Cl here, one Cl here. So it will be polydichlorophosphazine. Or if I say I have ethyl group here and ethyl group here, then it will be polydiethyl phosphazine. Next is sulfur nitrogen linkage, and sulfur nitrogen linkage represented like that, and the bracket will come here and the bracket will come here. So that compound is called sulfur nitride. sulfur nitride. A handout is given to you and it's already uploaded on the module. You have to read about sulfur nitride by yourself, so I'm not going to discuss about this anything. So you will read, and if you have any question you can send an email to me. Now the next is boron nitrogen. So the name says, so the backbone has boron and nitrogen connection. So look at here, this is a trimers 1 2 3, and that's how the boron continue from this side and nitrogen continue from this side. This is the structure of the repeating unit. So backbone contain boron nitrogen, and that's the way chain will continue. So remember here you should know how to write the repeating unit of each, number one. Number two, if I ask you to show me connection of at least 3 unit or 4 unit, you should be able to write correctly. Okay, because this is like a remote teaching. So if I cannot read and if I cannot see correct connectivity, I will simply cut that one. I will not accept that. You have to show me correctly, and this is nothing new. I discussed this in the class before the closure of the university, so you know all these connectivity how to show. Okay, and the next is sulfur. Only sulfur in the backbone. So you have sulfur here, so the connectivity of the sulfur here and here, and this is called polysulfide. And also you can also have polyalkene sulfide. So if you have polyalkene sulfide, then you have R and S. Means in the backbone you have R and S. So means like you have alkyl group and you have S, and that's how this connection takes place. Okay, so that's all the introduction of the important inorganic and partially inorganic polymer. Again, as I told you, you should remember what are the possibilities of which atoms are present in the backbone, what are their main family name, and what will be the new name if we change any of the substituted group, and how to write the repeating unit, and then how to write a dimer or trimer or tetramer or oligomer, or at least 10 unit if I ask you how to show. Okay, now this one inorganic polymer are also synthesized by the step growth polymerization, chain growth polymerization, or ring opening polymerization. Any of the three method can be used, and you have already studied what is a step growth polymerization, chain growth polymerization, and ring opening polymerization, maybe a little bit. So this will I will address mostly I will address the ring opening polymerization, because the step growth and chain growth you already know. So I'm not going to talk about why it is step growth and why it is chain growth. You already know. I'm only emphasizing on how these polymers going to produce, synthesize, and why some give you the linear polymer, some give you the cross-link polymer, and what are the modification and how they are, why they are important, and where you're going to use. So, important polymer which we're going to study, these three: polysiloxane, which is as say siloxane. So this is like a heteroatom, partially inorganic polymer, and polysilane, which has only silicon in the backbone, and then polydichlorophosphazine. Phosphazine means phosphorus nitrogen in the backbone. So these are the three. Whereas the polythiazole, this one I leave it for you to study by yourself. This one, no, not this one. Go back. Um, yes, this one, sulfur nitrogen, polythiazole or sulfur nitride. This one you have to study by yourself by the handout. It's a very small information. Okay. Now, let's go to, before that, I used to explain all these three topic on the board, but now this is difficult, so I add some new slide here for your help. Otherwise, I could simply give you that you already know how the synthesis takes place, so you can extract the information from the handout, that is from the book. But I put some important information that will help you to understand. But of course, you have to read that this topic from the book for complete information. Any questions can be asked, because this time most likely the online exam, so most question will be multiple choice questions, right? So emphasis will be on more their name, their repeating unit structure, and their uses, and how they are produced, right? Most very unlikely the mechanism will be asked, but mechanism I could ask in the assignment, or also deliberately a wrong mechanism may be uploaded in the exam and ask you if this is correct or wrong. So that's how I can judge you if you understand the mechanism or not. Okay, so now the synthesis of the polysiloxane. So as the name says, polysiloxane is the polymer that contains silicon and oxygen in the backbone. So it is prepared by the hydrolysis of alkyl siloxane or aryl siloxane halide. Means you have to use these material to prepare polysiloxane. Alkyl siloxane halide means you have R, Si and Cl or Br or I, like an alkyl halide. Alkyl halide formula is RCl, RBr, I. Here you will have R with silicon and then halogen. Okay, and an aryl silicon halide means you have aromatic ring, then silicon and halogen. That's the meaning of this. Okay, and these starting material, which starting material? Alkyl siloxane, aryl siloxane halide. These material are starting material are made by reacting silicon with either alkyl halide or aryl halide. So if we have silicon and then we react the silicon with alkyl halide, like for example CH3Cl, or aryl halide, for example benzene ring with with the halogen, then we can get this starting material. This is the starting material we need. This is not available. We have to make this by reacting silicon either with alkyl halide or aryl halide. So in order to make this one, we need to heat these materials, silicon and alkyl halide or aryl halide, between this temperature, and we use copper as a catalyst. And this is the way the starting material which is produced here is the best way to prepare methyl chlorosilane. When we say methyl chlorosilane or phenyl chlorosilane, what does it mean? So remember the structure of repeating unit formula of the polysiloxane. So in polysiloxane, methyl chlorosilanes and phenyl chlorosilane means, here look at here, this is alkyl silicon halide or aryl silicon halide. So when we say methyl chlorosilane, which means our alkyl group is methyl group, and we say phenyl chlorosilane, which means our aryl group is phenyl group, and the halide is chlorine. Okay, Cl, chloride ion. Okay, so that's a way. When you see the equation, you will understand it better way. So now look at this equation here. This is the one. So you have silicon and you have alkyl halide. Okay, I did not write here any name like methyl, ethyl or phenyl group, because this is the journal equations given to you. So but if it is asked to you write the correct equation, you have to look which compound I am asking you to prepare. Okay, if I ask you to make methyl, then you have to change the R with methyl group. If you see in the formula name isopropyl, change the R group with the isopropyl group. Or if I say phenyl, then you have to change R with the benzene ring. But this is a general trend here. So you know silicon is in group 4, so it has a 4 valencies. So that is why we have 4 possible product. First product is that all the Cl from here attached to silicon, so you get this product with the tetra substituted silicon. And the other case, what you get 1R and 3Cl. The other is 2R, 2Cl and mono substituted. Monochloro, dichloro, trichloro and tetrachloro product you may get. All these are possible, but not all of them will be suitable for the synthesis of the polysiloxane. The reason you will see here. Now this is the one, but this is the first step. You got your precursor. These are the precursors: alkyl silicon halide or aryl silicon halide. That's what you need, and these information which mentioned here is helping you to understand how to make these precursors or these starting material. Yes, this is obtained, but this is not this is the first step. Then these material undergo hydrolysis. So when you do the hydrolysis, this Cl will be replaced by OH. Okay, so when you have ROH, what you call it alcohol. Now you have SiOH, so this will be known as silanol. Like hydrolysis of these halides gives unstable silanol. OL means like an alcohol OH, and because of the silicon it's called silinol. Collectively it is called silinol. In the next slide you can see what are these silinol you will get. So if you use tetra substituted silicon, then all the Cl will be replaced by 4 OH group, one here, one here, one here, and one on this side. Okay, or you can write this way. Okay, the second is this is the tri substituted, so you get 3 hydroxy group. Now this is the di substituted group, you get 2 OH. You should be able to write with the proper bond. Like here, if I want to ask you to show the structure of 1 OH, you write 1 R here on top, 1 R in the bottom, 1 OH on this side, and 1 OH on this side. Okay, and then you should be able to write the equation correctly in the next step which you're going to see. And then you have this one the last one, which is the mono substituted. Now if you look at here, these are the salinol, which is unstable. This will undergo to produce the polymer. Okay, how? Condensation reaction. So if I take this monomer here and I take one more monomer here, so the OH from here and the H from here will lose the water molecule. That is why it is a condensation reaction, and then this O will be connected to the other part. Okay, this condensation reaction I already showed you how to connect the two monomer. Okay, now look at here. So all of them are not suitable to produce the polymer. Why? Look at here. Here this one this one give you a cross-link polymer. Why? Because the monomer functionality is 4 group, 1 2 3 4. So all directions the chain will grow and a cross-link polymer will form. Here what you will get here, again you will see you will get a cross-link polymer because the monomer functionality 3. The one chain goes this way, other chain goes this way, and the third can combine from top. So the cross-link form. So only this monomer will give you a linear polymer, give the linear polymer. What about the last one? Would it give the polymer? Answer is no, because the monomer functionality is 1. When you connect to the this one, then the dead end. Here you have 3 CH3 group, other monomer you have 3 CH3 group or R3 group, so that cannot further progress. So after the dimer, the reaction will stop. Okay, no polymer form, only dimer can form or can be used to stop the polymerization, and this material can be used if we want to stop this polymerization. So what happened when after certain time, when the polymer polymer reach the required molecular weight, we add this one additionally. So what it will do, it will attack at the end of the chain here and stop the reaction. So this can also be used as a terminator. And what is the purpose of this one? This can be used if I want to produce a cross-linking here. So after making this polymer, we can add some of this, and then it will start connecting the chain with each other to make a cross-linking, and the cross-linking is produced to make the strength of the polymer. Okay, so now after the hydrolysis you get this precursor, and now I'm going to show you how it is going to polymerize. So now you look at here, this unstable silinol undergo a condensation reaction to form a siloxane linkage. So this is the, you have, for example, I'm showing you, this is trimethyl trimethyl silicon chloride. Okay, so this is the one I'm using. I'm showing you this one, trimethylsilinol, which is this one, sorry, this one. So after the hydrolysis, what you get? You will get 3 methyl group or 3 R group and 1 OH, and that is shown here, which I was showing you. It will make a dimer, but this will show you how the silinol linkage will produce. So after hydrolysis you get this unstable one, and if you use 2 of these, so OH from here and the H from the other will lose a water molecule, and that's how connection will produce. Look at here, R, 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 and R. This is condensation reaction because a small molecule is produced, and this is dimer. But this dimer cannot further proceed because you have, so that is why this mono substituted salinol can be used for terminating the reaction. Okay, now the actual reaction with using the di substituted one can be shown in this slide. Okay, so as we know, this will give you a linear polymer, and the linear polymer can be can be seen from here. So this is the one you have. This is the way you show your polymer formation. So this is, for example, I replace 2R with 2 methyl group. Okay, so methyl groups, which is dimethyl. Okay, polydimethyl siloxane. So why it is called siloxane? Siloxane. Siloxane is the polymer name, and these are the 2 methyl group. That is why it is dimethyl, and it is the polymer. That is why polydimethyl siloxane. So first it will be hydrolyzed into OH and OH, and then you have to show the reaction this way, the way I showed you here. So one OH will combine with the H of the other OH and make this linkage, and then you will see an OH here that will combine another one and so on. So if it is asked, show me how the chain formations takes place, at least 4 or 5 unit, you should be able to write it, and you have learned this several times in the previous classes. Okay, so that's how polysiloxane is produced. Okay, now polysiloxane, this is produced here, and this is some information you have to read, important information from the book. Now I just put it some important thing here. As a general method of preparing polysiloxane, hydrolysis of the halide is not a satisfactory method. What does it mean? The procedure, which the method which I just showed you, is not a very satisfactory method. Why? What is the reason? Because once the trimer is formed or tetramers form, trimers means 3 unit, like that, 1 unit, and then you connect this one with silicon, same, and then another one, 3. So if you count from here, 1 2, and then you will have silicon here, which is number 3, and then you have oxygen is number 4, then silicon is number 5, and then oxygen is number 6, and this oxygen will go back and combine with silicon to make a 6-member ring. So if you have 3 monomer, 3 a trimer, then trimer go back to the first silicon and make a cyclic ring. This is the meaning I'm explaining. So look at here. This is, for example, 1 monomer. Then this is, you call it 1 carbon, silicon 1, then oxygen. What is the next? Silicon, that is number 3. Then what you will have? Oxygen, that is number 4. So it is a dimer. It's a dimer, and then after the dimer you move from here, oxygen, you will get to silicon. This is the number 5, and silicon connected to oxygen, which is number 6. Now this oxygen, instead of going to continue making the chain, it will go back from here and connect on this side of the silicon to make a cyclic ring. So the molecular weight, as long as you are doing the reaction will continue, but the viscosity of the solution will not increase, which means that since the viscosity is not increasing, which means the molecular weight is not increasing, all the monomers are converting in making the cyclic compound. And when this happens, when a trimer is formed or a tetramer formed, so trimer or tetramer eventually form the ring, 6-member or 8-member ring, and that's how the molecular weight does not increase. So that is very important to remember here. So this is the method to prepare polysiloxane, but this is not a very good method because of the formation of cyclic ring. And this is a very important potential question, why we do not see the increase in molecular weight, because of the formation of the cyclic ring due to trimer, or after the trimer form or tetramer form undergo the coordination and undergo cyclization. Okay, so how will you make the polymer then? Okay, so what happened now, after this reaction is done, you isolate this cyclic product by distillation, purified, and you get this cyclic product, which I showed you in the next slide. Okay, like this one, this is the cyclic product. You got it. As I told you, it could be a 6-member ring or a 8-member ring. Okay, and you take this cyclic product which you isolated it, and then you do one more reaction in which you have to open this cyclic ring. When the cyclic ring open, then you get a long chain polysiloxane, high molecular weight. So in this slide, it is showing that how you can do that. There are 2 methods to do. It is called acid catalyzed ring opening or base catalyzed ring opening. Okay, so the procedure is basically same to open the ring. So in the presence of sulfuric acid, a ring opening reaction will take place. So when the rings open, all the rings will open, and then all these open ring will combine with each other, and the long chain polymer will form. So that's the basic idea here. Okay, now, but in this case, Before that, what happened? Due to the cycle formation, there is no increase in the molecular weight. But now, once you do the acid catalyzed ring opening reaction to open the ring to get a high molecular weight, you get extremely high molecular weight, which is also not required. So you need to control the reaction to stop at certain point. So how would you do this one? For that purpose, what we do, after some time, we start adding this compound, which is called as hexamethylene disiloxane. Okay, this is going to be added in the molecule hexamethylene disiloxane. It is like a dimer. Hexamethylene disiloxane, what I'm talking. Let go back to this dimer, and then you'll know. No, not this one here. Sorry, this one. See, this is the dimer. So if you have a methyl group here, here, so how many methyl groups? Six. So this is called hexamethylene disiloxane. That's a compound we're going to use. Why we are using this one? To stop the reaction at certain point. And that's how the molecular weight cannot increase. And I told you before why it stopped the reaction, because no more OH on at the end. So reaction cannot continue. Okay, so you can read this one later on, and what is the property and why it is used, why it is important, everything you read here, and this I'm not going to discuss. Okay, now look at here, this is a cyclic compound, and that's a compound we are using, which I showed you, a dimer. Hexamethylene, 1 2 3 methyl group here, 1 2 3 methyl group here, Cl and O. So hexamethylene disiloxane, hexamethylene disiloxane. So this is a dimer of the product which I showed you. Now under H2SO4 use, so this is the ring opening reaction under acidic condition. So when you use the acidic condition, the ring will open. So you will get the OH here and OH here. So if the OH here and OH here is survived, then the reaction will continue. All the chain will combine together. So look at here. This is the OH here, here the H was here, and also here you have OH. Okay, OH on one outside and H on other side. Remember how to write the chain. So the reaction, when the dimer formation, OH from one side and H from one side, making the water molecule. That is why in the bracket, one side you will write the H outside the bracket, other side you will write the OH on back side. So what happened now, this molecule from here, this one, okay, this will come on this side and react. This will break under acidic condition, and this will come at this corner to block the OH. Now see here, after reaction with this OH, you will get silicon with one CH3 here, one CH3 here, one CH3 here. No more OH, free OH available, so no more further polymerization. So the reaction will stop. Same on this side. So that is actually used as a terminator to stop the reaction, and that's how we control the molecular weight. So we have polysiloxane synthesis, and then we notice that the molar mass, I mean like the viscosity of the solution, not increasing. Why not? Because after the trimer and tetramer formation, a cyclic compound start forming. That is why monomer consume, all the monomer consume, but molecular weight does not increase. So this is the problem of this technique, but no worries, because after that we isolate, do the distillation, unreacted selenol will be distilled out, and all the cyclic compound which have the a higher molecular weight will be settled down, and then we add the sulfuric acid into that solution, and this sulfuric acid do the ring opening polymerization. So this ring will be break, so the H will come here to make OH, and on this side you also get the OH, and then one chain start connecting, one 6-member ring will break, so you get hexamer, and then another hexamer, they combine together to 12 units are combined, and then 12 combined with other 12, and that's how the long chain will form. Okay, but that will give you a very high molecular weight. So during the reaction, we take the sample and figure it out what is the molecular weight. Once we reach the desired molecular weight, you could ask what is the desired molecular weight, any weight, whatever we want. If we are using as a hydraulic fluid, maybe not more than 10,000. So once we reach the, or we want to use a heating material, like remember before that, before the hot plate we arrived in our department, we used to use silicone oil to heat any chemicals or a beaker into that solution. Okay, and that purpose we need a little bit less viscous solution, so we have to stop the reaction at a required molecular weight. Okay, and then at that time we add these material. So once we add this material, it will block the OH from this side and this side, and the reaction will stop, and that's how you terminate the reaction. Okay, so this is the way. Now you got the polysiloxane, and this polysiloxane is a linear polysiloxane. Okay, now sometime we are required to make a polysiloxane, a cross-link polysiloxane. So instead of using a di-substituted selenol, we use a tri-substituted, and then a cross-link polymer can be produced. But once the cross-link polymer produced, you cannot give a shape you cannot reshape the material. That is why it is not very useful. So what we do, we prepared a silicon in such a way that a linear polymer we prepared, so it is easy to handle because of the viscosity, and wherever we want to use, we use it. But we add certain chemical which is called cross linker, something added into that, and cross linker, and then when this material is exposed to moisture or heat or something else, then it start cross-linking reaction. And after the cross-linking reaction, for example, if you have in your window something break and the air or light is coming and you don't want to replace the whole window, so you have heard that put some silicone. So what is this? If the silicone is already cross-linked, it is very difficult to put inside that small hole. So it is like a very viscous liquid you have in the tube, you just put it, and then after some time when you come, it's like a rock solid. So why it become rock solid? Because of this some reaction going on, and that is the cross linking reaction. So I am going to show you this one in the next slide. This is called room temperature vulcanization. Why? Because room temperature, because this reaction takes place at room temperature. Vulcanization means doing the cross linking. Okay, one pot room temperature vulcanization means you just have your material and just you expose this to atmosphere, and then the cross linking takes place. So you can read this material here, and that is why it is called RTV. So remember this terminology, RTV. What is the meaning? It is called room temperature vulcanization. And what material we use here for cross-linking? Cross-linking agent precursor, we use methyl triacetoxysilane. So methyl triacetoxysilane. So silane has 4 valencies, right? So one side we have methyl group, and other three sides we have triacetoxy group. So what this is going to do? Look at here, the tri is telling you after the reaction the tri group will block the will be hydrolyzed and give you 3 OH group, and this 3 OH group will start doing the cross linking. Okay, why can't we use the tri substituted selenol, which I showed you before here? Because if the free OH is there, then it will immediately do the cross linking right away, and which we don't want. So we use the precursor which is masked, which is hiding, and it cannot do until we want it to do. So that is why we use triacetoxysilane. So when this material methyl triacetoxysilane exposed to moisture, this triacetoxy group converted into OH group. How many OH group? 3 OH group, similar as I showed you in the previous slide. And then these 3 OH group start doing the cross linking with the polysiloxane polymer. Now look it into this equation. This is what I'm talking about. Triacetoxy. This is the triacetoxy group, and this is the methyl group. Okay. So so this one, and this is your polysiloxane. And polysiloxane, hydroxy terminated polysiloxane, means you have the OH group in the chain at the end, and this side on the other side. Okay, that is why it is called hydroxy terminated polysiloxane. So dimethyl polysiloxane, siloxane, but hydroxy terminated, so it have the OH group at the end. Means it is still active, it can further polymerize. And here this one and this one we added, and this is available in the tube. Okay, now because here the OH is masked, it is hidden, that's why it will not undergo cross linking. So you will keep the liquid like a honey, a viscous liquid in the tube. And when you expose this liquid into air, then what happened? The air will do this moisture from the air, hydrolyze this one, cut from here, and give you 3 free OH group like here. So this compound is exactly the same I showed you in the beginning of the lecture, where I showed you how mono substituted, di substituted, tri substituted, and tetra substituted salinol produce. So now this one, and this is your acetic acid, a byproduct. This will not do anything. Now when this will come here, this will react here. Look at here. The OH from here will take the H from here. Okay, one OH from here will take the H from here, and this will be connected. So this, look at here, this is the polymer chain SiCH3, and this is the O. This O, this is the O I'm showing you, and the H is gone. Now H will be reacting with OH to make water, right? So now this, see, OH from here and H is gone, so the Si is connected with the O. So this is the Si of the cross-linking precursor, and what you have onto this one remaining left with CH3, this is a CH3 and 2 OH group, which is one here and one here, and this will do the same. And you don't need to show all cross-linking, just this way you show. This will be continuation and this will be continuation with another chain, and that's how cross-linking takes place, and your silicon become harder. Okay, and this is very important reaction to remember. I may ask this one to show how cross-linking takes place in the assignment or in the exam. Of course, in the exam, if it is in the class, yes, then I will. But if it's not in the class, then I cannot ask this question to show how to do it. But I can show you one wrong or correct final product and ask you if it is right or wrong. This is the way I can ask, but most likely in the assignment this could be asked to show how to do this one. Okay, and this is called room temperature vulcanization. Now something about the glass transition temperature. G is stand for glass and T is for temperature, glass transition temperature. Okay, I ask you to, one of the group amongst you are writing an essay about the thermal analysis. So when you finish that essay, you will know what is this glass transition temperature means. But I'll tell you briefly here, because this is a very separate topic. But to tell you, when you have a polymer, all the polymer are exist in the glassy state. Okay, so when you start heating, then as I told you, all the polymer chain, one chain, second chain, third chain, all are stag on each other. Okay, and they are in the glassy state. So the temperature, when, like for example, if I say what is melting point, what is boiling point, so it's a change between the two phase, right? If the solid get into liquid phase, the point where the solid start getting into the liquid phase, that is transition, and at that time the temperature is called melting temperature. When the liquid start getting to the gaseous state, and then it is called the boiling temperature, the change in the phase. Here you have a glassy phase, and the next phase is the rubbery phase, rubber form. So the polymer start changing its phase from glassy state to the rubbery state, but that you cannot see by your naked eye. For that you need thermal analysis method like a DSC or TGA. By that you can see. So that is, I will left it for you, because that's a report I asked you to write. So then, so the simple is that what is the temperature? This is the internal motion. So you have one polymer chain, another polymer chain, and they are stag on each other. So once you start heating, then the temperature goes up and up and up, and then the polymer chain start moving inside. This is called internal segmental motion, which you cannot see by naked eye. You cannot see any change from the outside. If this, like as I mentioned to you, the ice start melting, you can see the water start boiling, you can see, but this motion you cannot see, the internal segmental motion. And the temperature at the time when this motion start, internal motion start, is called glass transition temperature. Okay, and this glass transition temperature sometime is high, sometime is low. So why it become high and why it become low? So now it's very simple. You have to concentrate on the on the definition. The definition says is the internal segmental motion. So look at my hand here. I have two chain. So if start moving, these chain are start moving, right? So when they are start moving, at that time the temperature is called glass transition temperature. Now, so if this movement take place very easily, no restriction, then the glass transition temperature will be low. And if this chain and this chain I am moving, but there is some cross linking or some bigger bulkier group or some other stuffs which I will discuss later on are there, and they are actually putting the hurdles and they are actually restricting the motion, then it will increase the TG. And what are those factors? One of the important factor is bond length. So as the bond length increases, okay, the glass transition temperature decreases, because if you have more bond length, the linkage between the two atom will be more fluffy, so they can easily move. So look at here, when you have carbon carbon backbone, then the bond angle 1.5 bond length is 1.54, and for carbon oxygen 1.42, for silicon oxygen 1.63. So the bond length is higher. Because of that, the silicon oxygen bond is more flexible, and that's why the internal motion is much easier. That is why the TG is lower, glass transition temperature lower. And so this is a reasoning question could be asked, why it is low? Because of the bond length. Higher the bond length, more flexible the bond, more easier will be the internal segmental motion, and that will responsible for lowering the TG. And it can also be explained on the basis of the bond angle. So as the bond angle increase, this will be the same reason as I discuss here. There are some other reasons as well. What are the pendant group you have? If the pendant group is bulkier group, then it will do the restriction. If the pendant group has so many branches, what is the effect of that? And so many other things. So that will be discussed in more detail when I will talk about the glass transition temperature in more detail. But anyway, in the writing report of thermal analysis, the group who is writing the report, they should have covered this part, and then you all know about that. Okay, now we will talk about some modification of the polysiloxane. So I'm not going to read all these things. This is, you can read. I put it the important point here. I will just explain it to you how this modification done and why it is important. And so here you have this this the precursors. Now what this precursor you should know. Now the methyl group is replaced with the phenyl group. So the is the aryl aryl silane halide, okay, or aryl silane or aryl trichlorosilane or phenyl. This is the phenyl group. So phenyl trichlorosilane, okay. Trichlorosilane, after hydrolysis, this will give you 3 OH group, okay, which means the 2 OH group can continue the chain and the third one can make the cross linking. Okay, this is the benzene ring. So when you do this polymer, suppose this is the first chain you wrote. So on the silicon you have 3 OH, 1, 2 and 3 after the hydrolysis, and this phenyl group will go here, or methyl group, but here we have phenyl group. Okay, now, and the similarly, this is a monomer, and then the second is a dimer, and then trimer, and the chain will form. Same, the another chain will form. The third OH group will combine, and that's how you will see a ladder type polymer will form. A ladder polymer will be formed. Okay, and this ladder polymer will form, and this is like a cis syndiotactic structure. You should know what is cis, but maybe you don't know about syndiotactic, and you will know later on in lecture 8 what is syndiotactic. But cis you should know. Look at here, this is the phenyl group and this is the phenyl group. If I go from here, these phenyl group are on the same side, so that is why it's called cis. Look at here, this is on the same side, it is called cis. But if it is above the plane and other is below the plane, then it's trans. So when you make a modification by using the aryl group, then you get a cis ladder polymer. And why it is called syndiotactic structure? Syndiotactic structure, there are three tacticity. One is called atactic and the other is called uh, Syndiotactic, okay, and isotactic, which means that if all this phenyl group in the chain are on the same side, all this phenyl group or methyl group or whatever the substituted group is are on the same side, either above the plane or below the plane, then uh, this is called isotactic, same side, isotactic. But if some are up and some are down, some are up and some are down, it's called atactic. So what is the syndiotactic means? Syndiotactic means one up and one down, and that is called syndiotactic. Now why it is called cis syndiotactic structure? With a cis anti cis arrangement, cis anti-cis arrangement fuse ring. So syndiotactic means now this is the first structure, and if you write another structure, in the another structure the C6H5 will be down position. That is why it become a syndiotactic. And because of down position, if you look this benzene ring compared to the other benzene ring which is down position, this will be anti-cis or trans. That is why it is called syndiotactic structure, cis syndiotic structure with cis anti-cis arrangement. So I'm repeating again. Look at here. This is cis, okay, and this is in form of tacticity. This is isotactic, right? If I'm looking only this molecule, but we have a long chain, so we have to look all of them how they are arranged. So this is cis. If I draw the same structure here, but in this structure according to this anti, so one of the C6H5 will go down. So if I compare this C6H6 with this one, this will be trans. That's why it's called anti-cis. And also it becomes syndiotactic because one up and one down. So that is why it is called cis syndiotactic structure. Okay, now other modification is introducing an aromatic ring in the backbone. Look at here in siloxane polymer, no aromatic ring in the backbone, only silicon, silicon, oxygen, silicon, oxygen. Okay, only silicon, silicon, oxygen. Look at it, silicon, oxygen, silicon, oxygen. Now we want to introduce an aromatic ring within the chain backbone. So what you do, you have to start with this monomer, again a disubstituted halide, and you use and aromatic ring like a benzene ring with 2H group. Okay, and this way when it undergo hydrolysis, after the hydrolysis this will connect to this part, look at here like this one, and this OH will continue the chain, and that's how aromatic introduce into the benzene ring. Now where this OH will go, this will connect to the next what, Si. So next Si like this one here, and then the reaction will continue. So that's how you produce. Now another thing is this, using a titanium a titanium metal in the chain. So again you start from the disubstituted one because the disubstituted give you the linear one. So when you do the reaction here, again you have 4 OR group, one on top, one in bottom, one on this side, one on this side. That will continue the chain. So the Cl will go with the R, and O is connected with the, so RCl will be the byproduct, and this O is connected to the Cl. So look at here, this is your siloxane, RSIO and O, because 2Cl. So 2Cl will be changed into 2OH, OH here and OH here after hydrolysis, and then this OR will take this H out to make alcohol, and connection will take place. So this is titanium OR, and two of the OR will replace with the H to make this connection, and that's how titanium is introduced. Why we are doing this, what is the important, where it is used, you should read. Okay, this reaction here also is called this reaction of the formation of the ladder polymer. This one I'm talking about 16.11. Look at here, uh, the synthesis of the polysiloxane comb polymer. A comb polymer can be made by using the macromer technique. And now you should know what is macromonomer. Macromer is a polymer chain which have a reactive chain N, and that can further polymerize. So look at this polymer. This is the polymer polysiloxane, and here we have a benzene ring, which is, if you just hide this part, if I cut this part, this will be what? This is your styrene. How you polymerize styrene? This is a free radical reaction, so you need initiator. So whenever you do this reaction, you need to put an initiator here, and then this polymer will start growing. So just you think that you are doing the polymerization of the styrene, and at the para position you have this polymer. That's the way you do reaction. So if you just if you cannot understand the equation this way, you just tilt this equation 90-degree, and then you'll know, like a styrene doing the, so polymerization of styrene, and at a para position you have this polysiloxane polymer. So this is another very important reaction from the examination point of view, to ask you this polymer and put the initiator and ask you to show how polymerization takes place. So this is one. Now this macromer, this is a macromer, because this is have a reactive chain end. Because of that, this is a one will be act as a monomer, but this is not a small molecule. That is why it is called macromer. Now the second, you have to connect what you will have here. Here you will have CH and then benzene ring, and entire everything will be same like that. This is the second, and then you have third, and then you have fourth. So that is why it is called a comb polymer. So one is shown here. The second, third, fourth, you should be able to write in your home how to do that. Okay, this is your job to do, and I may ask this question. And then the next is making a blockopolymer. A blockopolymer means introducing an ether into siloxane. So this is your polysiloxane group, and this is your polyether. So you take polyether and polysiloxane and you connect together, and you get a blockomer. This is the polysiloxane block, and this is the polyether block, and that is called blockopolymer. That's the modification of polysiloxane. Now, modification of the polysiloxane can also be used to modify the inorganic glass. Okay, so again you read this one. I am just explaining the equation. So inorganic glass. So for example, this is the tri-substituted silicon. Okay, so which is OR. So if you hydrolyze this one, you will get 4 OH group, that I already mentioned to you previously. Okay, so in the previous slide we have SiCl4. Here you have OR4 substituted group. So this will be hydrolyzed and you get OH. Okay, now this is can be pyrolyzed of the hydrolyze alone. So if you do the pyrolysis of this reaction, then you will get the glass, which is, you will get the ceramic, but which is an unmodified ceramic, and that have brittleness. But if you want to make a softer ceramic which have less brittleness, you just don't do the pyrolysis at this step. What you do, you take the polysiloxane polymer. This is your polymer, polysiloxane polymer, and in this, why we are writing this is outside, because we want to show how reactions takes place. Remember, in the chain growth polymer, I showed you how to show the termination reaction. Always write one unit outside the bracket so the actual reaction can be shown. So here I can write N-1, because one of the monomer unit I am writing outside. So this is, here is missing is N-1 at this point. So then you use the silicon which have 4 OH group. So what happened? 4 OH group. So one of the OH connect with this, connect this silicon. So this is connected to this, and how many OH left? 3. One on this side, one down, and one on this side. So all will do the cross linking or connecting the chain. Like from here, this will be continue same way, from here continue, and from here continue. Okay, now after that the same thing you will write here, everything will be same, and then you have OH. Now this OH can also be combined with another SiO4. So now this is connected to the Si, and this has 4 OH groups, so one is used connecting to that one, and 3 will remaining left, and this will be the continuation. That is why one of the monomer was shown outside the bracket so you can see how the reactions takes place. So one of the SiO4 will come on this side. So one OH will connect to this one, remaining left three, one here, another one here, another one here. So O is missing. You can write O here as well if you like. If you don't write, no problem, because it is shown here. So this is the same reaction. This is your SiO4. One of the O4 connected to this by reacting with this OH, losing the water molecule, connecting here, and 3 OH remaining left, and this OH will connect to another chain, another chain, and another chain. That's how the ceramics which is produced is the marriage between the ceramic and the polymer, and that's how it is called ceramers. The name is ceramers. Okay, ceramers, ceramics, and from polymers. So that is why it is called ceramers, and this has less brittleness. So remember the terminology ceramers, and you should know how to write the reaction. Now move on to the next one, which is polysilane. So I will go a little bit faster now. This polymer is produced by chain growth. The previous one, polysiloxane. So this is the basic difference from the mechanistic point of view. I don't have a chance here to show the mechanism, that's why I'm just avoiding this one. But the difference between the polysilanes production and the polysiloxane production is two. That one produced by the step growth condensation reaction, and this is produced by chain growth condensation reaction. So this is the basic difference on the basis of mechanism. Polysiloxane by step growth condensation, polysilane is by chain growth condensation. So this is a chain growth, and because initiator is used here. Why condensation? Because small molecule produce. Okay, because silicon has four valencies, so you can put two substituted group R and R, which could be two methyl group or methyl ethyl, whatever you can put, and two Cl group which can undergo reaction. So sodium will be used, that will replace the Cl, because if you put the water here, then this will be converted into hydroxy group, and hydroxy group will not give you polysilane, it will convert it into polysiloxanes. That is why this reaction takes place in absolute dry toluene, so no moisture required. Okay, so that's how the reaction will take place. So one Cl is removed, and then the first monomer connect to the second one, and then second to the third one. That is why it is called chain growth. So chain growth mechanism exactly the same. First you need initiation, then propagation, and the termination. Okay, and in this case we have silicon bond length, which is 2.34. So you just think, would it be, if we want to find out the Tg for this one, would it be lesser than the siloxane or higher? That's a question I leave it for you. So silicon bond length is 2.34, and silicon oxygen bond length you can check on the previous slide again, and then answer this question. If you want to find out exactly, if you have methyl group here and methyl group here, and in polysiloxane you also have methyl group, then which one will be more flexible and which one have less Tg? Okay, this is the way you produce an alternative synthesis of polysilane, which is a 5. This is compound is called polysilane, is the dehydrogenative coupling of dialkyl silane. So you can also use this chemical that have two H, like instead of Cl you have H, so you have to remove these two hydrogen. That is why it's called dehydrogenation or dehydrogenative method. Okay, but for that we need a metallocene catalyst. Okay, metallocene catalyst, which is I'm not really interested right now to teach you, but this is the only thing. Remember, if you have this monomer, then you require metallocene catalyst to make this polymer. Okay, a similar procedure has been used to prepare high molecular weight polystanase. What is this polystanase? Same procedure. Which same procedure? This method. Okay, or this method. A polystanase means you have, instead of Si here, you have Sn, tin. Okay, or stanase, and that's how you can introduce a tin atom in the backbone. Okay, now look at here. You can also make a polysilane instead of using only one type of substituent. Look at here. This is one monomer in which you have CH3 CH3. This is another monomer in which you have a CH3 and a phenyl group. Okay, so which means that you have to require two different type of monomer here. Look at here, in one monomer you have CH3 CH3, another monomer you have one CH3 group, other is phenyl group. So you will actually get a copolymer. So this is actually a copolymer. Copolymer is produced. Why we are producing this copolymer? This compound is compound number 6, which I somehow I forgot here to copy. So polymer 6. Okay, and this polymer is very much similar to styrene. Look at here, this is phenyl group is benzene ring. So if you have a benzene ring here, so the benzene group is like a styrene. So how the styrene connected in a similar way. So that is why this compound is also called polystyrene. Okay, and why this is important? This is important because it can be used for doping purpose. Okay, doping is the process, like we can use this is used for because of this phenyl ring, it is photo it can undergo photo degeneration under the influence of UV radiation. Therefore this is interested for the UV active photosynthesis. Okay, but the most important is doping. If we put arsenic pentafluoride, take the arsenic pentafluoride and mix with this compound 6, then it becomes a semiconductor. So important, this is the important thing. This polymer which we produce, a copolymer, can be used as a semiconductor, but not by itself. First you have to mix this one with the arsenic pentafluoride. So what is the difference between this one and carbon carbon containing semiconductor? Is that because this one has only sigma bond. So the sigma bond, it shows that, which indicate that there is a considerable delocalization of sigma electron along the backbone. So the sigma electron can delocalize along the backbone to conduct the electricity. On the other hand, if you have a carbon carbon polymer which required the conjugated double bond, so until and unless you have a double bond, single bond, double bond, single bond, delocalization if not there, then you will not see the conduction of the electricity. So this is also can be used as a semiconductor. Now the last one is the polyphosphazine. Polyphosphazine is the ring opening polymerization. A polyphosphazine, as the name says, polymer. Phosphazine means the polymer that have the phosphorus and nitrogen in the backbone. So this is the general formula of polyphosphazine. Phosphorus with the nitrogen, and these are the two substituted group Cl here. Okay, but how you prepare this polyphosphazine? This is the monomer which will be used. How many Cl you have here? 1, 2, 3, 4, 5, 6. That is why it is called hexachlorocyclo. Why cyclo? Because this is a cyclic, like a benzene ring. Okay, instead of carbon we have phosphorus nitrogen, phosphorus nitrogen. So that is why cyclo. Hexachloro, 6 chlorine, cyclo, triphos, 3 phosphorus, 1, 2, 3, triphosphazine, 3 nitrogen, 1, 2, 3. That is why it is called hexachlorocyclotriphosphazine. So in the exam, the name can be changed very easily. I can change chloro group into bromo or fluoro group. So the name should be hexabromo or hexafluoro or hexaido. So look at the name correctly and write the structure in the exam or assignment correctly. I will not accept that, oh, I thought it was like that and I just put Cl. If it is asked fluoro or bromo, it should be changed. Okay, triphosphazine, and of course the internal structure will be same. So this is the monomer which is used for preparing this polyphosphazine. This is a very important polymer, inorganic polymer, which I'm going to discuss now. But this monomer is not available, so it should be prepared by reacting this compound phosphonitrile chloride trimer. So you take this one trimer, and when you react, then this monomer is produced. But here I'm not talking about this one, how to make. You have to start from this monomer, which is hexachlorocyclotriphosphazine. chlorocyclotriphosphorazine. So remember, like a benzene ring. So when you heat this polymer up to this temperature, okay, you get this polymer. Okay, this is the repeating unit of this polymer. So of course here the important point is this, how the mechanism of this is very important. Okay, and this I am showing you in the next slide. So what happened now, once you heat, this bond is ionized, so this will be cut off from here. Cl will be leave as with the negative charge, and the P will be leave with the positive charge. That's the first step, ionization. This will be break. C will leave with the negative charge, leaving the positive charge on phosphorus. That is the start to remember. And I may ask you to show this mechanism in the assignment. Okay. Now look at here. So I showed you the first step. The Cl is gone and you left with positive charge on this P. Now you write another monomer, same monomer. Now here the nitrogen has a lone pair, you all know, and the lone pair is the nucleophile. So this nitrogen will attack here to make a connection. Connection with what? Connection with this P. So how to write after the arrow? Just write this molecule as is, which you wrote it here. As is, everything same. And then write the connection. So this arrow telling you make a bond between this P and N, which you made. This is the bond between P and N. You make the bond between P and N. Then what you have? You have P with a double bond with 2Cl. So you have N double bond with P with 2C, and then you have N double bond P 2C. So you have this one N double bond P with 2C, and then you have N double bond with P with 2C. This one. So what happened when this nitrogen attacking here to make a connection between P and N? The bond between this P, this N and P will break in favor of N. So that is why here when this bond will break, in this chain will get a positive charge. So that should be clear. Now this arrow is telling you, you bring another monomer like this and do the same. That is the third and then fourth, and then you make several arrow and then you write final product like that. This is the mechanism of the ring opening polymerization. Okay. Now after this uh, you can see some other product here, why this is this why we are doing this one and what is the importance of this thing here. Now look at here, you could ask this question to me, okay, this is done, but why only one Cl break, why not other? Yes, the answer is correct. Yes, your question is right. Other Cl can also break. That is why if you do the heating for longer period of time, then this Cl or this Cl or this Cl may ionize and cross linking takes place. Read this point. Chain branching may then occurs to the similar mechanism, which the mechanism I showed you. So a branch can start from here, a branch can start from here, but not very close to each other because of the steric hindrance. So yes, branching may also takes place. Okay, and that's why that lead to the cross linking. Okay. Now this is the thing. Now why this is polyphosphosines are important. So this product which is produced here, this one is not very good, not very stable. It's not a very stable, but this is very important product to be used, but it is not very stable. So if it is not very stable, so what happened? Because when it is exposed to the moisture, undergo hydrolysis, it undergo radially hydrolysis and converted back into phosphate, ammonia and other byproducts. So this is not very stable polymer, but it is very important for some application. So the question is here, how to make them stable? This is very easy. Now you look into the product. This is the product. If you replace the Cl, these two Cl with a suitable group, then it becomes stable. And here it is shown in this slide here, how to make it stable. It is, however, can be converted into more stable derivative by replacing the chlorine atom with alkoxy group. Alkoxy group means RO, or arylo oxo group, oxy group like benzene ring with O, or amino group. Okay, and this is the way we can get all this stable product. So now look at this one. This is your polyphosphosine. So if you react this polyphosphazine with alkoxide, sodium alkoxide, this R can be methyl group, can be ethyl group. So depend what the question is asked. In the question, if it's representing methyl, so you have to put methyl here, not R will not be acceptable. This is a journal presentation, and it should be absolute dry condition should be used, and then Cl will be kicked out and Or will come in this place. Then this polymer will be very stable. Same here, if you use secondary amine under THF, then this will bring the NR2 here, NR2 here, and this will become stable. So here is the phosphorus oxygen linkage, here is phosphorus and nitrogen linkage. But if you want to bring a phosphorus carbon linkage, then you have to start the product from the F substituted product, Cl substituted product, Br substituted product, or I substituted product will not give you PC, phosphorus carbon linkage. In order to get a phosphorus carbon linkage, you need to start with the difluoro substituted product, and the material will be different. Alkyl lithium or alkyl magnesium will be used again under dry condition. THF will be used, and you get this product. So this is the, suppose this is CH3, so this is the carbon phosphorus linkage, this is phosphorus nitrogen linkage, this is phosphorus oxygen linkage. Now all these are stable product which is used for certain application. Now the question you could ask, when this is the stable product, why can't we start from here in the monomer instead of using the Cl in the beginning? Remember, this is the way we prepared this polymer. This is the polymer prepared here. So why can't we have Or here already? Or R or any group, whatever the, or N group, whatever the substitution I showed you there. Why can't we start from here? The reason is that we cannot do this way, because when we have those substitution which we mentioned in the other slide, okay, then this monomer become very stable and it will not undergo ring opening polymerization, and we cannot get the product. That is the reason we have to first make the product and then stabilize it. That is the reason we cannot do the direct polymerization of the substituted monomer 7. We cannot. Okay, so that is the reason we cannot directly do this way. Okay, now another thing is that if you, these are the two other product, like if you start with this monomer, instead of one phosphorus will be replaced by sulfur, then the polymer is called polythiophosphazine. So we have introduced sulfur, sulfur is called polythiophosphazine, and if you replace the S with the carbon, then it's called polycarbophosphazine. So these are the two things in this slide you have to remember. So if you replace S, then this will be the product. If you replace C, then instead of S you write C. Okay, this bond should be here. So there is a mistake, it's not here. This bond should be between P and Cl. So these are the other product can be prepared, and what are their importance you can read here. But the most important thing which I would like to mention of this polythiophosphazine product is the this reaction, introducing the substitution of this group. So we have this polyphosphazine. Now remember this reaction, this is the stability reaction. Okay, this is your polyphosphazine, and this polyphosphazine reacted with what? Sodium alkoxide. So this alkoxide, now we are showing here what alkoxide we are using here in this reaction. This one, these are the two alkoxide we are going to use. So polyphosphazine as a variety of application, especially this one, these two, like see here we have trifluoro, there are the two alkoxy group we use, fluoro alkoxy substituted group, fluoroalkoxy substituted group. So this is fluoroalkoxy group. So instead of CH2 CH3, one of the H3 will be replaced by fluorine. So this is called trifluoroethoxide. Trifluoroethoxide. Another one I'm using is heptafluorobutoxide. So where these monomer, these will be changed. Look at here, in the place of R, trifluoroethoxide and fluorobutoxide. So in place of R you change this thing and absolutely the reaction will be same. Okay, now since we are using, suppose if we are using trifluoroethoxide, so you will get trifluoroethoxide here and trifluoroethoxide here, because only one you are using. But since we are using two different trifluoroethoxide or heptafluorobutoxide, that is why it's a copolymer, will be replacement like a copolymer. So look at here, you have to write three repeating unit. In one, both of the Cl will be replaced by trifluoroethoxide. So trifluoroethoxide. The other one you have to use heptafluorobutoxide, and the one with mix. So that's why you have to show three unit for this polymer. And why this polymer is important, all these effort why we did, only because of this, preparing this polymer. Why? Because this polymer is have, because of its fluoro group, it has a greater flexibility at a temperature lower than minus 77 degrees Celsius, and this polymer is stable up to 9 to 300 degree Celsius. That is why this can be used for under and for the elastomer used in the fuel lines and sealants in the Arctic environment. So if we take any ship or plane or something in the place where we have this lower temperature, this polymer will be used for protecting the sealant, protecting the fuel line not to choke, because this polymer survive this low temperature and this high temperature. That is why this is very, very important, this polymer. Okay, now detail of these polymer are mentioned, the handout on these pages you have to read in more detail. But what I did, I put all the important informations here. At least you should remember all these things and read sulfur polysulfur nitride by yourself, because I did not discuss this here, and because it's only one page, and rest of the other important thing I put it here, but some of them you have to repeat. And now this one, what I'm going to talk a very small thing about the glass. This is just reading material. Water glass you probably have already studied in Dr. Massimiliano class or Dr. Yunus class, but just a little information. Difference between glass and ceramics. So glass is the amorphous non-crystalline solid material, and these are the raw material used. Okay, and different additives are added to give different color, and glasses are typically brittle and optically transparent. Okay, one of the important glass is the soda lime glass. Most of the time this type of glasses we use. So here you have to remember basically what is the basic difference between glasses and ceramics, and and what are their important ingredients. So where they are used, these are the important places these glasses are used. Also they are used as a reinforcing material. Okay, glass fiber you have noticed in the laboratory, which we can also use for insulation purpose. Okay, now, borosilicate glass. Then borosilicate glass is the glass is very one of the important glass category, because this has a very high this has a very low coefficient of thermal expansion. Okay, that's because of the low thermal and expansion capacity. It has a resistant to thermal shock. That is why this type of glass we use making the making this is also called a pyrex glass, and this is used for making the household cooking ware and reagent bottles. Okay, these are the and the ceramics, as I told you, that this is also inorganic, but it's crystalline oxide material. Ceramics are the crystalline oxide material prepared by the action of heat and subsequent cooling, and they are brittle and hard, but they are strong in compression, weak in shearing and tension. So if you have a ceramic tiles and you just put little hammer, it will break. Okay, this is the one. Now, so how to make it little bit stronger? This one, Usually we prepared it traditionally the ceramics prepared by clay material, which is this one, and nowadays we include aluminum oxide, which is also called alumina. Okay, and this is the modern ceramic material, classified as advanced ceramics because it include silicon carbide or tungsten carbide. These are the two material we mix with the material which we mentioned in the previous slide, and then the ceramics are produced, and these ceramics are very good for abrasion resistance. Okay, so what is abrasion resistance? I leave this for you to find out. If it was a normal class, I explain it, but now because it's remote teaching, so I leave something for you to find out. So abrasion resistance, okay, therefore used in applications such as the wear plate or crushing equipment. So this is actually giving you the information what is abrasion resistance. So if you put some little effort here, you can find out. Anyway, if you don't understand, you can send an email to me. Okay, and this is the advanced ceramic which can also be used in medicines, electrical and electronic industry. So this is the first and second part of the lectures. Inshallah, I will make the video for the third part, which is mostly focus on the organic polymer, in the next class. Thank you very much. Have a wonderful day.